Hello, this short video is speaking about amplitude modulation. We'll look at three areas. First we'll define amplitude modulation in the time domain. Then we'll look at the problem of crossover distortion and how this limits the modulation factor. And finally we'll look at the power spectrum of an amplitude modulated signal. Amplitude modulation is the easiest way of imposing an information or a message signal onto a much higher frequency carrier wave. The three graphs below are an example of this. The first signal is a low frequency signal, which could be an audio signal, some music or a telephone conversation, which will extend from DC up to a maximum frequency of a few tens of kilohertz, for example. The second graph is a much higher frequency carrier wave, and this could be at a radio frequency. It could be at hundreds of megahertz or gigahertz. The third is the amplitude modulated signal, and you can see that the amplitude of the carrier wave has been adjusted so that it tracks the message signal. This is the message signal up here, and the amplitude of our carrier signal has been adjusted so it tracks the information signal. This dotted line is just there so you can see what the information signal looks like. Mathematically, these are what the different components look like. First we have a carrier wave, which is oscillating at some carrier frequency. Omega c here is the carrier angular velocity, and it's related to the carrier frequency by this multiplication factor of 2 pi. All this is to do with units. We know that you can only take the cosine of an angle. So omega c is an angular velocity, and when multiplied by time gives you the total angle by which this cosine needs to be calculated. The amplitude here is the amplitude of the carrier wave, hence the lowercase c. So this is our carrier signal. It carries no information. It's only used to lift the frequency up to the band we wish to use. The second equation is our equation for a amplitude modulated signal. There are two parts, the amplitude and the cos of our carrier frequency is the carrier part of the modulated signal. The part in these brackets here is the message or information part of our signal. You can see that we've taken our message signal, we've scaled it or multiplied it by this number, which is the modulating factor, and we've added it to 1. The reason for the complication inside this bracket is to avoid a problem known as crossover distortion, and the next slide will show you an illustration of that. You can see that the modulating factor, if it's equal to 0, means that your modulated signal doesn't have any information in it, because 0 times our message signal is 0, so we only have the carrier component. As the modulating factor gets larger, then there is ever more information in our modulated signal. Now, clearly, we want as much information in the signal that we're transmitting as we can engineer. Otherwise, we're broadcasting informationless power. So these graphs illustrate the problem of crossover distortion. The first graph is an information or message signal which has both a positive and a negative part to it. Now this is commonly the problem with audio signals, which oscillate around a DC level of 0, and so for every positive lobe there's a negative lobe. The second graph is our carrier wave at some much higher frequency. Now if we multiply the message signal by the carrier wave, then we get this modulated signal at the bottom. Now if you imagine you're demodulating to try and extract the information again, one way of doing that is just tracking along these upper peaks, and you can see as I track the cursor along here, it tracks the same part of the information signal from high to low. But problems occur when the information signal crosses the zero axis. At that point, the amplitude appears to start increasing again. What's actually happened is that the amplitude has gone negative. So here you have a negative amplitude cosine wave, which is just the negative of a cosine wave. And at this point, you've gone through a phase change of 180 degrees. However, if you put this signal through a AM demodulator, you get the wrong information signal out. You get an information signal which is right here as it tracks down to the zero axis, then rather than going negative, it increases again. That gives you the wrong answer. And if this is a telephone signal or some music you're listening to, it would sound very bad indeed. So, to avoid this, we take our information signal, we scale it and shift it up around the level 1, so that we get a shifted and scaled information signal that is always positive, i.e. it doesn't ever cross over the zero axis. When we do that and then multiply by our carrier wave, we get this graph C, where now if you join the peaks you get a curve which matches the curve of the information signal, and the information signal can be retrieved by demodulating, and so really joining these peaks together, and then undoing the shift and scale to bring the information signal back down to be centered around DC. To avoid crossover distortion, we need to ensure that 1 plus the modulating factor times our message signal is always greater than 0. It's greater than 0 for all time. Now generally your message signal will be oscillating around DC, such as an audio signal. And so this constraint is equivalent to the constraint down here, because usually the message signal, the maximum and minimum values are just the positive and negative of each other. Right, so both these constraints ensure you don't experience crossover distortion. So that's what AM modulation looks like in the time domain. What does it look like in the frequency domain? We need to know this because if we're sharing spectrum with other systems, we want an AM modulated signal which will occupy some known little bit of spectrum, and so the other frequencies can be used by other systems. We need to know what the power spectrum looks like so we can manage interference between different systems. So, the first equation is just the expression we have for AM modulation in the time domain. We've got the message part shifted and scaled in here, and we have a carrier part, which is this cosine part here, for some high carrier frequency. Now, if we convert this into the frequency domain, so that's what this expression means. That means that these two descriptions are equivalent. This one in the time domain and this one in the frequency domain. So we've used this curly symbol here to represent the Fourier transform. So this expression in the time domain can be thought of as being made of 3 parts. It's got the amplitude part, which is just a multiplying constant. It's got the message signal part, shifted and scaled. And it's got the carrier frequency part, which is this high frequency oscillation. And these 3 parts are multiplied together. In the frequency domain, this is equivalent to convolving together the Fourier transform of the message part and the carrier part. The multiplying constant just remains a multiplying constant in the frequency domain. So, Fourier transform of our amplitude modulated signal is the multiplying constant due to amplitude. The Fourier transform of the message part convolved with the Fourier transform of the carrier part. Convolved, because remember, multiplication in the time domain is convolution in the frequency domain. Next, we look at the Fourier transform of these 2 parts individually. Firstly, we look at the Fourier transform of the message signal. We have 1 plus a constant times our message signal. So the Fourier transform of 1 is just our delta function, which is our big spike, centered when our angular velocity is equal to 0. So this delta function is this arrow here, which represents a function that goes all the way up to infinity but has area 1. Addition in the time domain is just addition in the frequency domain. Multiplying by a constant in the frequency domain is still a multiplying by a constant. And we'll say the Fourier transform of our message signal is this function here. The capital S and the omega tells us that this is the Fourier transform of our message signal. So graphically, we're going to assume that our message signal is band limited, i.e. it goes from DC up to some maximum angular velocity omega max. And because of the way we define our Fourier transform, that means that it's centered on DC and goes from minus omega max to plus omega max. It's been scaled by this constant, the modulating factor, and we've added this delta function to it. So, remember the delta function comes from the Fourier transform of the 1, the scale factor and the additions have just come down, and the capital S is the Fourier transform of our little s, which is our message signal. Right, so that is the information carrying part in the frequency domain. And actually it just looks like our original message signal spectrum scaled and with a delta function put in the middle. Next, we look at the carrier frequency. Now, it's just a simple cosine, and this is one of the Fourier transforms that we looked at. The Fourier transform of a cosine is our cactus, i.e. it's two delta functions, one at the positive carrier frequency and one at the negative carrier frequency. And there's a scale factor of pi, which we never really worry about. Next, we need to convolve this thing, which is the information part, with this thing, which is the carrier part. This is relatively easy. You remember that if you convolve anything with a delta function, then you just get a copy of the anything centered on that delta function. So we have two delta functions, one at the positive carrier frequency and one at the negative carrier frequency. When we convolve our message part with this delta function in the positive carrier frequency, then we get a copy of all this centered around omega c, our carrier angular velocity, which means we get a delta function at omega c, and then we get a copy of our message signal that will go from our carrier angular velocity down to minus the maximum angular velocity in our message signal, and all the way up to our carrier frequency plus the maximum frequency present in our message signal. And the same thing occurs centered around our negative carrier frequency. So this graph illustrates what it will look like in the frequency domain. You can see that we've moved all the information from being centered around DC to now being centered around our carrier frequency, omega c. And we have this spike, this a lot of power being broadcast at our carrier frequency. And the rest, the spread, is due to the information that we're broadcasting. The wider the bandwidth of our information signal, then the more the bandwidth is of our modulated signal. This big expression at the top is just a way of describing the four components you see down here. Firstly, the two delta functions at carrier frequency and minus carrier frequency. This is the delta function at the positive carrier frequency. You can see the brackets goes to 0 when the omega is equal to the positive carrier frequency. And this is the delta function at the negative carrier frequency. This is our message signal spectrum centered at the positive carrier frequency, so it's this one here. And this is our message spectrum centered at the negative carrier frequency. So this one down here. You'll never be asked for this expression. So, an important thing to note is that the spectrum of our AM modulated signal is twice as broad as the spectrum of our original message signal. Our original message signal only had positive frequencies extending from DC up to the highest angular frequency present. But our modulated signal has information in all the positive frequencies from the carrier frequency minus the highest frequency present in our signal up to our carrier frequency plus the highest frequency present in our signal. Right? So this range is twice omega max, which tells us that half the bandwidth of our AM modulated signal is carrying redundant information. Now that is wasteful and expensive, and as engineers we're going to have to do something about that.